Okay, everybody knows there's an exam tonight, 7 o'clock. It'll be similar in style, easier, I think, in content than the last exam. Don't worry, everybody did pretty well in the last one in spite of the fact you didn't score that highly. This exam will mostly test the second third of the course, the material we've covered since the last exam, for the most part. All right. So today we're going to talk about neutron stars. Yes? Sorry? It's going to cover part of today, just a little bit. All right? Not relativity or black holes I'm going to talk about. Okay? And we'll talk about neutron stars more. Okay. This is about some of the material we want to talk about. Yes? Oh, yes. Can you hear? It says it's on. Hey. Can you hear me? All right. This is a spectrum of M87 shown on the screen. The M87 is a giant elliptical galaxy we'll talk about later. We suspect that, we know it harbors a gigantic black hole. How do we know that? With the Hubble Space Telescope, they put a slit, or right here they took a spectrum, and here they took another spectrum, right around the nucleus of the object. And they found that the spectrum of one was redshifted relative to the other, which is blue shifted. This is one spectral line. The shift was substantial, and what it means is that the material in there is swirling around. The size is determined by the distance from the nucleus, that plus the distance of the object. That determines the size. And so you have the ingredients, v squared equals gm over r. You know what v squared is. You know what r is. You can solve for m. The mass of this thing is 1 billion solar masses, 10 to the 9th solar masses, that is in the form of a black hole. So black holes that's evidence for it, and black holes are pretty strange, and they're very common in the universe. There seems to be a black hole of about this size or smaller in every galaxy, or virtually every galaxy we look at. And that's a puzzle that we must understand, or astrophysics must understand, and really does not understand it as of now. Okay, the next question I want to address is the issue of neutron stars. Neutron stars are leftovers from supernovae, particularly type 2 supernova. Now that's the supernovae that has an iron core and a wedding cake of material on top of it, and it's in the center of a massive star. They seem to burn to what is called a neutron star. Now, what is a neutron star? We'll talk about as we go on. The core of a neutron star is less than 3 solar masses, we think, or otherwise the star will collapse. So upper limits to the mass of these stars is about 3 solar masses. A neutron star would be if you take the entire sun and shrunk it down to the distance between here and the Bay and San Francisco. It's a ridiculous amount of mass to cram into such a small space. Remember, a white dwarf is if you take an entire star and cram it down to the size of the Earth. Neutron stars are much, much smaller. Much, much smaller. How do we know they exist? I mean, it's a ridiculous idea. You can't see one. How can we know they exist? So let me try to say, well, how you tell it. The neutron star, if it exists, is very dense and very small. And they are seen to rotate very, very rapidly. The whole star, the whole neutron star rotates in 0.03 seconds, up to 4 seconds sometimes, slowly. But many of them are very fast rotators. So we'll try to see what that means. All right, magnetic field. These are very, very strong magnets, incredibly strong, and is very strong compared to the Earth, who has a field less than 1 Gauss. Here is a neutron star. It's seen in the X-rays, and this is a supernova that blew up in 386 AD. It's in our galaxy. Now, the supernova, as I said before, will leave a gigantic cloud of material. This cloud of material contains a lot of heavier elements and is accelerating away from the central region of where it occurred. This one is the Crab Nebula, the one that I said you should have seen from here, from the Earth, I mean from the northern hemisphere, and they don't report it, at least in Western astronomical literature. The amount of energy was gigantic, and this is where all the elements heavier than iron are created. Now remember I said iron is the element that's most tightly bound. You cannot add anything to iron. You cannot add to it or subtract from it and expect to get any energy out. But if the star is exploding and you have a ton of neutrons that are free as the material disintegrates, you have free neutrons, and think about there's no Coulomb barrier for a nucleus to absorb a neutron. After all, there's no positive charge on the neutron, or negative charge, and so it goes right in. Whereas, you know of the proton, it's got to overcome the incredibly strong electric repulsion of the two species. But neutrons have no such electrical repulsion, and they can be absorbed readily. There are no free neutrons in stars, none at all. They don't exist because they're so reactive. Within nuclear reactors on the Earth, they're incredibly absorbed quickly, very quickly by anything. So the neutrons are free, and they're absorbed by the iron, and the iron becomes heavier. Adds, and it makes super neutron-rich elements, super neutron-rich. And by a process of decay, it forms all the elements we see. It forms all the uranium. All the gold in the universe is made in supernova while the star is exploding. So that means that the gold is somewhere in there. These supernova are incredibly important because they are the major production of heavy elements on the Earth. They're really the only production that amounts to anything. So the fact that we have anything in our bodies that's heavier than hydrogen and helium means that there were supernova around. And supernovae are really, really important. But in our galaxy, they don't occur very often. There's only been 4 of them in the last 1,000 years. So the supernova just occur, and they blow up. Now, here are some other examples of supernova. Here is a supernova seen in the radio. Where is this? This is one called Cassiopeia A, 10 light years in diameter, this thing. Here is the same supernova seen in the X-rays. So Each of these things is expanding at a rapid speed. And the supernova are beautiful objects of this expansion and the solutions of mathematics and everything. Here is another one. This is the one that Tycho, and he of course didn't see this picture. He saw a bright light in the sky, and it was there for a month. This is what has become of that bright object. The grass on the outside is colored blue if it is 20 million degrees, green if it is 10 million degrees. This star has, it's not really spherically symmetric, but it is roughly spherically symmetric, and has all these little nodules in it. This is the formation of heavy elements right in front of us. They are fantastic if you can find them. So this is an incredibly important element former in our galaxy. Okay, now supernova. Once the supernova has blown for a while, the gas that it blew out becomes thinner, and it's called such things as the valent nebula. This is Tycho supernova again, but the thing is diffuse, and this will go through the interstellar medium, pollute the interstellar medium with heavy elements. Those heavy elements then go into the next generation of stars. For example, our sun has a lot of things on it. It has uranium, it has iron, it has chromium, it has anything you can think of. All the elements are on the sun. You can see it spectroscopically. All those elements were made in other supernovae. Our sun, therefore, is not a first-generation star. For that reason, it's a second-generation star. So first-generation stars were made when the universe was very clean. But after a time, the universe gets dirtier and dirtier. If you call iron as dirt or anything, it's heavier and heavier. So the pollution of all that stuff makes the elements heavier, makes them heavier and heavier. All the stars that we see out in interstellar space have no reason to be the same abundance of elements as the Earth. It's on.
Yeah, getting a low level on this thing. Sorry, keep coming about me.
Oh, no, that's fine.
Let's see.
Is it working now? Oh, maybe, am I supposed to turn this to some value? I thought this was that's something else. That's for this thing, yeah. What is, I should know about this. Okay, is that better? Well, it's on. That's all I can say. Okay, so the supernovae are seen in the sky. They're not that common. They are strong radio sources. Low. What's the matter with this thing? Hold on one second. Okay, let's try. Okay, so supernovae, come on, produce these fantastic remnants. Here is one of the crab. Here is one of Cassiopeia A. Look at undents, and look at the scale. This is a logarithmic scale. 1, 10 to the minus 2, 10 to the minus 10th. So after a supernova comes off, you end up with Everything, oxygen, neon, magnesium, silicon, sulfur, argon, heavier than iron you see. And that is because of this rapid process of neutron absorption in the, of the iron nuclei. Absorb it, absorb it, absorb it, and then it decays by weak interaction, decays and transforms to iron, transforms to uranium eventually. It's got enough stuff in it. Yes? A heavier element, all this is occurring deep in the supernova core. That's where the neutrons are abundant. However, we do see that on the envelope of a supernova, you can see it. You can see that the heavier stuff is on the inside, the lighter stuff is on the outside. So it's really pretty good. It's amazing. And when you get the spectrum of these supernovae daily as different things are heated or not, it's astounding what you can see in them. Of helium nuclei right into the precursor. It just formed, just like having in the big stars, form the precursors. So these are than whatever is between them. And iron's a little bit higher. Okay, so, boy, this thing is not working. Why not? Should be working. All right. These, where they make all the oxygen and neon, those are more abundant than the other stars. Okay, the heavier than iron, they're produced by the neutrons that come out, and they're absorbed, and they can absorb neutrons and go all the way to the top of the atomic number. Okay, now I'm going to show you, this is an amazing picture. It's made at the University of Chicago. They've taken a white dwarf and they are going to explode it. Now what happens is burn, 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 burn. The white dwarf has carbon and oxygen in it, and the white dwarf burns, and here is the remnant of it, showing the circled around. All right, the hot bubbles rise to the top, all right, the carbon burns, the hot bubbles rises to the top and surrounds the entire star. Now the reason this happened is the carbon was initially degenerate, they say. And the carbon burns explosively when it gets hot enough. And when it's degenerate, it can get very hot very fast. Note that it's not spherically symmetric at all. And it burns and burns and burns really fast. Now, this is a process that happens in the advanced stages of a big star. And I said, well, carbon burns, and then eventually some other stuff burns. Oxygen burns, the other things burn. But some of these elements burn explosively. Now, one thing you would expect is eventually it'll burn all the way to iron, okay, as it gains a little bit of energy. Now, the iron, we won't gain any more energy by burning it, but the carbon, you gained a little energy. Now, what would happen? You see, it burns so asymmetrically, and the asymmetric burning means that the momentum transferred, if all of it ejects this way and throws it off, then the neutron star has to eject the other way, because momentum has to be conserved in the entire process. So what would happen? All right. So when the white dwarf explodes and burns incredibly fast to a neutron star or something, really a neutron star, what you see is that the star should be moving fast, because you put the gigantic jet engine onto the neutron star, powered it, and say, well, now let's move, let's see what we got. October 96, September 99. It's moving in the sky. This motion is very fast. It's moving like 600, 700 kilometers a second, whereas typical stars move around at 100. It has been accelerated by the rapid burning. And an example of the burning was shown in the previous picture. It's non-spherically burning, and it makes it into a jet. And the thing, bang, flies off in that way. The rocket engine that worked on the neutron star is what happened. It's pretty incredible. Why this isn't working. Now next, I want to talk about something called a pulse. It was discovered by accident in the 1960s. And they saw, this is a time lapse, 3.33 seconds, here to here to here to here. The pulse is strong pulse, strong pulse, strong pulse, but then there's a weaker inner pulse between. These pulsars were known as LGM. This is something pulsing at us. Little green men. Okay, so these stars are known comically as LGM. Better than that, they're known as pulsars. This is the pulsing of the Crab Nebula, right in the center of the gigantic nebula. There's the Crab Nebula. This is a pulsar. Is an object somewhere right in the center. I don't know which star. So this thing pulses. Most of the pulsars we see are not pulsing in the optical band. They're only pulsing in the radio band. But we detect them. We detect hundreds of them now. What do they mean? All right. So the pulsars have, this was discovered by Jocelyn Bell and her advisor. There's a picture. All right, the pulse occurs 1.3 seconds, and they determined it was 300 parsecs away. And what was the source? Now, 300 parsecs is very close to us. After all, the galaxy is distances of 10 kiloparsecs. So 300 parsecs is indeed just a fraction of a kiloparsec. All right, so this is Jocelyn's accident. However, her advisor won the Nobel Prize. Go figure. She didn't win a prize for this. All right, what is a pulsar? So let's think what the pulsar can be. First thing you think of, well, let's just do quick, and then it spins around. The hot spot is saying on the equator of the white dwarf, and it's well, let's see. It's about the size of the Earth, and the orbit has velocities moving at the speed of light. Not that that's possible, but just imagine it. Okay, now, the circumference of that star is 2 pi times the radius. And the radius is the radius of the Earth. And that's about 40,000 kilometers all the way around. Okay, so that's the circumference of the star. And we know that the circumference is equal to the time for spin once times the velocity. All right, you're going at a velocity, and it's equal to the time to spin once. All right, so we know the velocity. We say the velocity is up to the velocity of the speed of light. The circumference, we're putting in a number, 40,000 kilometers, which is characteristic of white dwarfs. And therefore, solving it, you solve for tau, that's c over v, c divided by the, 40,000, and that's 1.13 seconds. The crab, however, moves around in 0.03 seconds. In other words, let's imagine it is a neutron star. A neutron star is 1,000 times smaller than a white dwarf. Therefore, it doesn't have any trouble making the thing spin that fast. This was a proof, a demonstration that these pulsars are unlikely. Well, there are some that are much faster than the crab, and it's impossible for them to be white dwarfs. So this had to be something denser than a white dwarf. The only thing denser than a white dwarf is a neutron star. It can't be a black hole, the hot spot. A black hole is black. It doesn't have any other characteristics. No anchor point. So it can't be a black hole. It had to be a neutron star. All right, neutron star is small enough, and this is suggested as a stable state of condensed matter by Oppenheimer. Oppenheimer was a professor of physics at Berkeley. Go Bears. Okay, so this is done by people here. Now, he didn't live to see this. He didn't live to see that he's right, but he was pretty sure he was right on the basis of the fact that you could make equation of state that it was kept the star stable, even though it was only 10 kilometers in diameter. Incredible. So that is Oppenheimer's characteristic was this is a neutron star. Now, a neutron star is just like the electron star that we saw before of a white dwarf have in the same way that electrons have. And that was the next stable particle that you could imagine. Neutron degeneracy is the same process, only for neutrons. He discovered this, and he discovered mathematically how this would work. The entire mass of a neutron star. A black hole can't be the anchor, or can't be the spinning object because there's no way to anchor the light that you see. But it doesn't say what this thing really is. What is a neutron star? Here's a drawing we make of these objects. A star, the neutron star, is spinning really fast. Incredibly fast. At the same time, 10 to the 13th times the magnetic field of the Earth. So the magnetic field spinning a bit off axis. If it were on axis, it would be right up north and south, but it's spinning around. The beam radiation finds it easiest to leak out of the north or south pole of the magnetic field. The entire thing is like a lighthouse. The lighthouse goes once, every time around, you see it. The bright light is when you see the light directly. The less bright light, remember the inner pulse, is when you see the other side of the neutron star and it's not as bright. So one side is bright, the other side is faint. Yes? The magnetic field can be thought of as the following. If you had the Earth and you shrunk it, the magnetic field has to be conserved quantity. It's a half Gauss, and as it shrinks, the magnetic field can be thought of as the following. You can draw a set of lines. Draw a set of lines for the field, and they're conserved as the star shrinks. So the star starts off with the lines spaced here, say at a few kilometers, and then they shrink, and then the lines are much more dense, and it has to increase as the square of the radius. So as the star shrinks, the number of field lines increases as the square of the radius, and the increase in field lines is exactly what it would take to have a weak field, say a Gauss field on the original star, collapse by 1,000,000, and then compress. As it goes down, it increases by 1,000,000 squared, or 10 to the 12th. And so the big magnetic field is simply a consequence of flux conservation, which has to occur for these stars. I won't tell you more about flux conservation, but it is a consequence of electromagnetism. Intense magnetic fields, which completely govern how the object works. Okay, so these objects are just amazing. Here it is pulsing around. There's a ton of energy given off by the object. Every second, this thing is swarming material. Yes?
So one of those poles is brighter than the other?
Yes. That's what we think it is. We're not certain. This is just an artist's drawing that is coming out here. It really can be different. It could be curtains. It may not look like this at all. It's very probably it doesn't look like this, but here's a drawing that gives you some idea what's going on. Now here's something that's even more spectacular. On the left-hand side is a picture of the Crab Nebula in the X-rays. On the right-hand side is the same object in the visible light. And you can see all these bands coming off. These are really incredible pictures. They were hard to produce. Remember, the cycle time is 3/100th of a second. So they put a bunch of pictures together to make them bright enough. What it is circling around and putting out magnetic fields or something. We're not exactly sure what's happening, but they are pulsing. And it pulses from the optical all the way through the X-rays. Tremendous amount of energy is being exerted by this pulsar. It's just spinning, spinning, spinning. And by the magnetic field, it's energizing the nebula around it. So they are amazing objects. All right, so this is a brilliant picture. The mathematics of this sort of thing was worked out by a professor in our department. He was able to, this was quite a triumph. All right, so pulsars and neutron stars. Okay, so all pulsars that we know of are neutron stars. They're all neutron stars. But neutron stars are not all pulsars. There are many faint collapse things that are not pulsars. It has to be spinning fast, and it has to be young enough to be spinning fast. Some are a little bit quiet. Okay, this radiation seen in the visible and radio frequencies is something called synchrotron radiation, and it's a common radiation given off by particles by particles moving close to the speed of light and bending a bit. So, all right, this is and it is a well-known process. The emission is mostly radio. All right, and if you're going to see a neutron star, it depends on the geometry. If you're not looking, if the pole doesn't point to you, then you don't see it. If the pole points another way, if it's pointing north, you won't see it. If you're looking at the side, you won't see it. So a lot of neutron stars won't shine at us. All right, so we don't see it otherwise. All right, neutron star ages, they spin down. So it took a lot of energy to light the nebula. So as the nebula is lit up and lit up and lit up, the neutron star loses energy slowly. Now, the youngest, therefore, it's not surprising that the neutron stars that are very young have the shortest periods. They spin. We've seen a few occasions where the neutron star doesn't spin up, doesn't spin down continuously. It seems to cause the glitch. How can this thing be spinning slowly and then spinning fast? The glitch is caused, we think, by a moonquake, or a neutron star quake, I should say. Not an earthquake, but a quake on the object. It sort of cracked as it was spinning down and spins at a somewhat different rate. At least that's the thought. So Those glitches happen once in a while. Now, there are some pulsars that were discovered that are moving very, very fast. They're spinning so fast it's hard to believe it. These were discovered by a group here at Berkeley. They worked on special instrumentation and took this to a big national radio telescope, and they found pulsars that are spinning amazingly fast. Now, these pulsars are found primarily in binary stars, and they're not sure how they're made. But the thought is that they are in a binary star, a stream of material flowing to the neutron star. The material flows into it in a spiral orbit, and it makes the neutron star spin up. The material comes in with angular momentum, and it transfers it to the neutron star. And this can make it spin incredibly fast. That makes the neutron star, if it's spinning that fast, it's now going not to relativistic speeds, but the outer surface of the neutron star is moving really fast. It's amazingly fast. Okay. So while the material is swirling around, it's getting hotter, and it will eventually do something like a nova, replace this neutron star with a white dwarf. And that accreted material, and once in a while it blows up, giving off this radiation of a nova. This sort of object should probably do the same thing. You would expect it to have something. You would expect this thing to blow up in the same way, and it does. These millisecond pulsars explode, and they give rise to, they burst, but they're such high energy, they don't burst in the optical region where you can see it. They burst instead in the X-ray region. This is confirmation that they're neutron stars, confirmation of the general idea, confirmation of how nova work. It's confirmation of a lot of astrophysical theories and mechanisms. So this is one way we know that that's appropriate. Okay, do X-ray binaries go nova? They accrete onto this neutron star. It's worked out. The neutron star is level about 1 meter thick of hydrogen on the surface. Once the temperatures reach incredible temperatures, 10 to the 8th degrees, the material fuses instantly. We have other things that are really crazy. Every few hours, every few days, a star that's just this neutron star and then it bursts. Neutron star and it bursts. And we think that they're caused by this continuous accretion of material onto a neutron star. Now, to see something weird, I should turn this light off. This is Eta Carina, up in 1840. Okay, and it left behind this gigantic homunculus. This is known as a homunculus. What does homunculus mean? Anybody heard of that word? All right, I'm going to turn the lights down a little bit. Okay, this is an amazing object. What is this thing is thought to be 100 solar masses. And the 100 solar mass object is so large that they're not really stable. The center blows up and they're kind of chaotic. Very hard to calculate what is expected. But this star is having indigestion. It's not eating the material, accreting onto it very well. It has, you can see it's got two regions, two peaks. All right. It's emitting this way and that way primarily. It's thrown off a lot of gas. is material to make a gigantic black hole. We think. This will eventually explode, and if this thing blows up in the next 50 years, you'll get a chance to see it. And this would be pretty spectacular to see. This is a real candidate. Okay, so now let me ask you a simple question. Supernova 1 and supernova 2, we talked about what they were. Let's jog your memory. Is supernova 1 a neutron star? And supernova 2 the burning of a black hole? If it's a neutron star or white dwarf, massive star and onion skin layers, blah. Take out your cards. Come on. A few cards not showing yet. I don't have any extra cards here. It's all right. That's good. Got it right. I like that card too. So white dwarf, accreting white dwarf is what makes type 1 supernova. And massive star in onion skin layers is what makes with all that chaos, it shows up all the iron core. That makes a supernova. This is not really proven, but that is the going hypothesis now. Okay, I'm going to skip this movie. Next, I want to turn to black holes. Black holes are a neutron star is rather small. A black hole is even smaller. And the black hole is finally the end of the line. Okay, if the neutron star cannot exist if the star is too heavy, we think that the upper limit to the mass is about 3 solar masses for a similar reason that Chandrasekhar felt there was an upper limit, or showed there's an upper limit to a white dwarf. Same idea. And this was known, this is what Oppenheimer worked out. He knew that, but it depends a bit on some issues of heavy material. He wasn't quite sure what it was. And we aren't sure today. Okay, now, last time I spoke about this potential. The potential is a quantity, a dimensionless quantity that you use to measure the energy of the explosion, the energy of the binding of the surface. In the case of a black hole, you have the potential is 1. That means the escape velocity is equal to the potential. It's there. Okay. Now, this is by definition a black hole. It's black because you look at it, you don't see anything. Nothing can escape it. You can't. The light cannot escape from the surface. Therefore, it is black, and it's a hole. A hole is a black hole. Okay, this region of space is so dense that the modification to Newtonian gravity is very extreme. Newtonian gravity doesn't apply anymore, but you're not surprised, and it doesn't really matter. Newton was very far from trying to use his theory around a neutron star. He never heard of neutron stars. Now, the question is, what's a black hole? A black hole is a region that has, as we said, you can define the energy of a surface. That's the energy of a ball at the surface. And we'll set that to 0. And we're just at rest on the surface. We're not moving. And if v is velocity at the surface of the planet, and you say it's just at rest, if you have just enough energy to get up, but you can't really get away, then the energy of being 0 means velocity is this written like that. And this is something worked out, commented by Pierre. All right, Laplace thought that, okay, you can imagine a mass of any mass and you can shrink it. And he said, well, what can you shrink so that eventually the size is something so that the escape velocity, or the escape velocity is the speed of light. And he said, well, this is the radius. And the radius turns out to be 3 kilometers. 3 kilometers for the sun. That is, take the entire Earth and squeeze it down to a radius of 1 centimeter. That's pretty good. Neat trick. That would contain the entire mass of the Earth and would be a black hole at that point. There's not much danger the Earth will turn into a black hole. Us had the right answer. The reasoning wasn't quite right. And this was first worked out by Schwarzschild immediately after Einstein published his theory. Scientists started looking at it and wondered what else it contained. The event horizon is which you cannot tell what's going on. Something on the inside of the horizon can wave at you, say, in that sense, we are cut off from anything going on in the center. We can't see it. And so it's properly called an event horizon. That's the Schwarzschild radius, black hole, event horizon. All right, so now what about a photon? A photon at the surface, we know that the photons climbing out of a well are redshifted. When you climb out of the well of the sun, the photon's energy is redshifted. Not so much, but it is redshifted, and you can measure it. When you climb out of the black hole, the photon never makes it, and if it does, it has 0 energy. Energy gets redshifted, 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 further, until it comes out with 0 energy. In other words, it doesn't come out at all. So infinite redshift. All right, the total loss of energy of the photon is another definition of what happens. Warp space-time about an object, as we know, and even light is affected by gravity. That's what Albert told us. And he showed that mathematically, and people who mathematics eventually say, yeah, you're right, Albert. Any of the students will in the class. It's pretty neat. All right, now the neutron star, or the black hole, warp space in a big time. Here's a flat piece of space. Remember, this is 2-dimensional space that should be thought of as a 3. The radial distance is something you can measure, very straightforward to measure it. But the radial distance is difficult to measure when you're talking about a black hole, because this goes all the way down to infinity. The man falling into a black hole and it crossing the event horizon gets spaghettified. That's a verb. It's a kind of curious verb. He gets spaghettified in the sense he turns into a strand of spaghetti. Perfectly sensible verb. Is that it's there? All right, so that's that. Now let's think of some other things that are kind of curious about falling into a black hole. In a probe. You'll say, on your frame of reference, it may take moving slower. And he says, well, it took 15 seconds instead of 50 seconds. All right, so it's moving slow. The light coming out is redshifted, all right? And eventually it gets redshifted so far that the probe becomes very faint, very faint. The mothership probe, apparently, he sees that in infinite time, he sees, eventually it's getting fainter and fainter and fainter, but he never, now that's what the man on the ship says. The man probe and never crosses. The man in the rocket ship that's going in a finite time. Bang, he's inside. Never to be heard of again. But he managed to infinite time to somebody on the outside. Pretty weird. Okay. Any volunteers to go into a black hole? You know, who does that in Star Wars or some crazy right through the horizon, and you're in. And all right, so let's see what we got. The clocks beat a little slower than Jupiter's because of the potential of the sun. So what happens at the sun? Black hole. Green or blue? Not everybody's holding their cards up. Red, green, or blue? Okay. It's not blue. They don't run faster. And so that's very important to remember. The black hole changes the star, but doesn't change the orbits of things that are far away from the star. There's no difference. It's just very centrally condensed, same old boring orbits, you know. Okay. Now, how can you find black holes? Well, there's a black hole seen here. There's a black hole right there, Cygnus X1. And Cygnus X1, you see roof, but it's larger, was thought to be indication of material raining down to it and giving off the X-rays on a very short time scale. That's probably the best evidence we're going to find. Now, since that time, there have been something else. There have been these events called gamma ray bursts, GRBs. A gamma ray burst occurs out in space. We thought that they were occurring. We didn't know where they came from. But now we know they come from, not sure where it comes from. Typically, you can measure the gamma rays within 3 or 5 degrees. You can't measure better than that. And within 3 or 5 degrees, there are billions and billions of stars and galaxies, and you don't know what the hell is going on. But they managed to satellite. They had a device. They had a gamma ray detector, and then it would switch instantly to here's a source that was located. This is an optical picture, okay, at a very high redshift very far away. Since the 1960s, there have been detectors of gamma rays in the sky. And they detected a few events a day, and it's very hard to focus, so circling around the Earth. When a nuclear bomb goes off, it emits tons of X-rays, enable the satellites to time the arrival, and they could locate where it was coming from, and they were expecting cheating by the nasty Soviet Union government. The paranoia never resulted in the cheating, seeing any cheating of things, but they did see these bursts, and they couldn't figure them out. They were coming from outside the moon, further away than the moon. So how did they do that? And then they saw them again and again and again, and then they realized these are astronomical sources. Nobody suspected them before, but astronomical sources were detected and seen, and they are now seen to be seen anywhere in the sky. That's isotopic, which are forming black holes instantly or quickly. Here at Berkeley, looking for them, looking for signatures of gamma ray bursts. We'd like to know what they are. Are they, I mean, these are rare events, but they're fascinating nonetheless. Now, I'm going to next turn to the center of our galaxy, the optical region, because of all the obscuring dust. There's a lot of dust on the way to the galactic. It obscures everything. All right. So it's interesting to ask what is there, because it's very, very strange. Okay. The center of the galaxy in the X-rays shows a source. In the radio, it shows a source. In the optical, it doesn't show. Well, this is the infrared. Shows these strange lines. We think those are lines related to magnetic fields. Okay. All right. So they're bright. 20 years, people have used this Keck telescope. That's the one owned by the University of California. Here is a picture of the Keck telescope, a field of view right here. These are the stars in the center of the galaxy in the infrared. This is a star, this is S2, and they've mapped over that time, they've taken pictures, looks like it, around Sagittarius A star. Now, a homework problem is going to ask you to calculate the mass of the planet. And when you do that, you'll find an interesting number. Okay. These measurements are made in the infrared, passing within 1 to the 6 million solar masses. I'm sorry, 2.6 at 10 to the 6 solar masses. 2 million solar masses in the form of a black hole, right at the center of our galaxy. That is awfully incredible. Okay? So the question is, what could be so small yet so massive? Can it be something else than a black hole? And people went through all the exercises, and there's a lot of stars. And you take this picture, and the stars are all different. They all move. And here's a picture of the center of the galaxy. All right. So you measure these fast-moving stars. This is the star S3. They've now observed it to go more than once around the orbit. It's now going a second time. Here's the other stars they've observed. Most of them are incomplete orbits, but they have observed. This is done by Andrea Ghez, a woman astronomer at UCLA. All these are all orbits around the Sagittarius A star. There are many anything in the center of the galaxy, but that's it. You have to look at it. It's a pretty neat object. Okay, now some of the black holes, some of those things have incredible bipolar flows. This is M82, and this red part is a line of hydrogen, Balmer, all blown out from the center of the object. It's pretty amazing. Here is our galaxy, a fictitious drawing of the gamma ray burst emission from the center of the Milky Way, 50,000 light years, and here's the sun. This was seen by my former student, Doug Finkbeiner. He was a great student. It's wonderful to be saw. He detected this thing. People didn't realize what it was. And it is a gigantic bubble of gamma rays from the center of just tons and tons of energy. How does this work? Okay, and you know what the exam form will be.